Now that the assembly issue is resolved, the supplier can start producing the subassembly. Since this subassembly isn't rigid, an inspection fixture will be fabricated. Then, a measurement system analysis will be performed to determine if the fixture operates as expected. The tooling engineer is creating the control plan on the CAD model of the fixture and providing a complete inspection project to the tooling operator so he can build the fixture.
That's right. I have the fixture fabrication project created by the tooling engineer here, and it contains the fixture datums, it has tooling balls, and it has a sequence that will guide the operator during the contact bolt adjustments. I have uploaded the project to data loop for the operator. Using the search and data loop, the operator can easily find the project of the fixture. Once the project is opened, the operator can click on New Piece. First, he is guided to probe the initial datum planes. Then, using the Build Inspect tool, the operator is guided for the first measurement of the contact bolts. At which point he can see the required adjustment in height for each contact bolt. The fixture can be adjusted with shims for each contact bolt to get the proper height. And at the end, a final measurement is done. And the project is uploaded to data loop.
Hey Keith, hasn't Innovametric released Polyworks AR recently? Wouldn't this be a good application for it?
Yes, I think this will be a great application for the Polyworks AR by using the Microsoft HoloLens. Check this out. Okay, this is a very small fixture, but imagine this process on a large aerospace fixture or a car body framer fixture. It's very interesting to have the results directly on the real part and no need to actually jump back to your computer every time.
Now that we have our fixture precisely built, the next step is to measure parts with it, right? Not exactly. It might be a good idea to verify first if our measurement equipment is repeatable. How are we going to do that? We're going to do a repeatability study. I'm sure many of you already know about repeatability studies, but just to add some context here, the study consists of the operator measuring the same part 10 times using the same measurement equipment. Factors such as the measuring device, the fixture, and even the clamping sequence are taken into account during the study. The goal of the study is simple. We want to measure the equipment variation and make sure it represents at most 20% of the characteristics tolerances. This 20% is a rule of thumb. It can be more or less depending on the applications. This value must be calculated for each key characteristic on the control plan. Another way to express the equipment variation is the gauge capability index. An index above 1.33 means that the gauge is capable of measuring the characteristic. Obtaining repeatable measurements is a challenge. Operators without adequate guidance can introduce variations in the measurement process. Extracting measurements on scan data requires fine-tuning measurement parameters to get the optimal results. Variations will be detected, and you need to understand the source of these variations. Finally, performing the repeatability study itself generally requires exporting the measurement results to a third-party software to finalise the study. Keith, can you show us an overview of how you would perform an efficient repeatability study on this part using Inspector, Data Loop, and also Report Loop?
Of course. The control plan is used to determine the key characteristic to test during the repeatability study. We have created the inspection project that contains the necessary features, trim edge comparison points, and sequencing. The sequence is built in to the template, and it will be important when we analyze our repeatability study results. We've also created an Excel template for our repeatability study. Once the measurements are complete, we will use Report Loop to analyze our results in this template. And when everything's prepared, we will upload the inspector project to Data Loop. The operator first searches, then downloads the inspector project from Data Loop. Because the nominal project was created, all he needs to do is create a new piece. The sequence begins with the guiding instructions demonstrating the proper mounting and clamping procedure. Then the tooling bores are probed, and the number of points to probe is defined with guidance. Scanning begins, and our operator follows the feature scanning guidance, measuring until the proper coverage is reached for each object. A boundary scan will be used to measure the trim edges and holes, while a surface scan will be used for the constraining planes and other plane features. The scanning guidance reflects this accordingly. The part is removed from the fixture and replaced in between each of our 10 trials to make sure that the process of mounting the part into the fixture is considered as well. And once all 10 pieces are complete, our operator uploads the project back onto Data Loop, so the data becomes accessible for the tooling engineer. So I've got word from the quality team that all 10 measurements are completed and have been uploaded to Data Loop. So I've logged in and downloaded the project. I can see that all 10 pieces are in the project. So now I'm ready for the repeatability study. I'm going to use the Excel spreadsheet provided by Polyworks to calculate variability. So all I need to do in Excel is connect to Polyworks. And you can see that the current open piece in Inspector is displayed in bold here. So I'm going to prepare this sheet for specifically the counter sinkhole 1 measurement. So for my features branch, find counter sinkhole 1. I can, for example, insert the nominal value into my sheet, and I can insert my measured value in here as well. And that's going to be our first of 10 trials used for the repeatability study. Now the link is made between Excel and Inspector for this value, I'm going to be able to add the other links automatically. This report loop tool will add all the links in the application in appropriate cells for all the trials in my Inspector project. This spreadsheet calculates the equipment variation as a percentage of the control's overall tolerance. What we want to see is a value of less than 30% of the tolerance used by the equipment variation. It also displays the values from the project on an IMR chart, or individual moving range chart. And that's about done there. So I can see that the equipment variation makes over 400% of my allowed tolerance. I have more equipment variation than my overall tolerance here. I will need to verify the reasons why. On the IMR chart, there is a value that stands out, trial number 6. The normal value is 6.35, and on the measured here, it's more than 9 mil. So I should probably start by investigating that particular piece in Inspector. So if we go back into Polyworks, jump back into trial piece number 6. And then let's zoom into countersink hole 1. And you can see here, we have a problem with the hole. I know that this hole is extracted using boundary scan points, and it seems that the cause for this this issue is false boundary points around the scan area due to these holes. I can verify this by showing you the points it's used to measure with. So review, deviations, restore, and you can see there it's using all these points away from the actual hole itself. So what I'll have to do is modify the extraction parameters. So if I right click, go to properties, jump into your measurement tab, and let's reduce the max distance down to 1 mil so it's not searching as far from the hole. And as you can see there, that has fixed the issue there. Okay, now I need to make all these same changes to all the other pieces within Polyworks. Again, in Polyworks 2020, Inimetric introduced a new tool which allows us to propagate piece changes across all pieces. So I can enter that through the bottom right hand corner. I have quick access to the configure propagation, and I'm going to create a new template. I can name it whatever I like, make sure I've got all my pieces selected, and just OK. This new tool in Polyworks 2020 is a powerful and welcome addition. It makes all the changes for me automatically, eliminating the need to make the same changes manually across multiple pieces. And now the propagation is configured, it can perform it. This was the #1 request from existing customers, from you. It was a great deal of work to make it easy to use and well integrated with both small and large projects in mind. You just saw how easy it was for me to set up, right? What makes this new tool so powerful, not only are new objects propagated, but also parameter changes to existing objects, new control views, and, you'll love this, report modifications. Polyworks documentation lists all the changes that can be propagated. Polyworks certainly goes a lot faster than I could manually and makes no errors. This is the first release of their new propagate tool, and their software architects have already started to work on improving the performance of this. So stay tuned to the intimate releases. When the propagation completes, the modification to all pieces completes the modifications to all pieces. Because of the link between the control in Inspector and the spreadsheet cell was established when the template was first filled in, the cells can be updated with one click. So if I go back into Polyworks, so let's go ahead and update the worksheet. So let's see how this affects the result of my repeatability study for that particular control. Again, report loop updates the values for me. Once again, this is no longer manual and error prone. The process is automated and no more exporting and results and copy and pasting values into the cells manually. Human error is removed from this update of all values for all pieces, and much faster than can be done manually. Okay, and that's about done. I can see that my range value is much better using the proper extraction parameters. And reviewing the other results, I'm very pleased with the outcome of the repeatability study. We have now less than 30% of the tolerance used up by the equipment variance. The repeatability spreadsheet and the trend charts provide discrete information about part variations on feature locations like features and comparison points. Inspector also offers a tool to illustrate this. It's the Surface Data SPC tool. If I go back into Polyworks, we can go into our Surface Data SPC tool and just disable that, initialize. Wait, that to initialize. This tool will show the gauge capability values of the whole surface and not only a discrete value at one place. It's like having the entire scanned surface displaying repeatability. This is actually applying lots of comparison points across the surface of the reference model, i.e. the CAD model, and then measuring each of those points against each of the scans. And we can see there we have a CG and CG, we can have CG and CGK values, a gauge capability points at any point on the scan. Zoom in there. We can see form variability across all pieces caused not only by the measurement device, but also by the fixture design. We might want to revisit the design of our fixture as the clamping is deforming the part and causing variability issues. And and that would have been hard to see without the help of the Surface Data SPC tool. Not impossible, but this color map makes it stand out and obvious to make my analysis much easier. Uploading the project to Dataloop will make this color map visible for everyone in the web interface as well.
Thanks. In reality, at this point in the process, the supplier would have to modify the fixture design and adjust the clamps and locating pads to get better repeatability. The repeatability issue was crystal clear in the colour map that Keith just presented to us, but let's assume here everything was good. What would be the next step?